guys. Let's see. I had a few questions during office hours. Anybody else have questions from all the homework that you're definitely doing? No? Okay. Let's see. So I think last time, did we finish that? Yeah, maybe we should do one more example from 5.2. And then we'll get to 5.3. Yeah. Okay. Yeah, let's do one more thing. Let's see. Let me find a decent. Yeah. Oh, okay. Real quick, a couple things. This symbol here. Remind me what that represents for us right now. So really, f prime represents slope. What does that represent? Don't read it to me. Tell me what it means. What does it mean? What is it telling you if you do it?
Oh, area under curve.
Area under f from a to b. I love it. So I'm given a function. And one thing I haven't really focused on too much, what are my functions here? So I have to kind of expand how I say this. It's not really the area under f, it's the area between f and the x-axis. So if this was a graph representing how our profit is changing over time, is this a good place for that to be? No? So if I integrate it, I'm going to figure out how much overall profit I've taken in. So in this instance, I will have been losing money, yes? So the area would be negative. Now for real life objects I can touch and hold, negative area doesn't mean shit. It's just, what the hell is that? Is it like whole stuff? What is it, right? But for math, this could represent the rate of change of something, and it could come out negative. It just means you're losing whatever that is, right? In this case, money. So negative area in mathematics is fine if I'm talking about some thing that I could lose, right? But you can't tell me that this triangle has a -7 feet squared area. Right? You guys see the difference between the two things? Okay. Some teachers are very reticent to say negative area, which is silly. Negative area, it's fine. Okay. So this represents the area between the x-axis and this function from a to b. I like it. Okay. What would this be then? Can anybody tell me what the number answer is for that? I didn't tell you anything, did I? What's A? I didn't tell you. What's F? I didn't tell you. I don't care. So explain to me again in terms, what does this mean? The area? Under the curve between F and the x-axis. From what to what? From A to A. So if I don't move at all, how much area have I accumulated?
0.
Okay, good. Minus. Right. Okay, I like it. Now, if I have this, so here's 1, 2, 3. If I have this, how does that relate to this? What's the relationship between this and that?
The answer is going to be the same, just opposite sides.
Because what do A and B do when I'm trying to do the summation stuff? The stuff we all love, right? The infinite something. What do A and B do? What do they set up? What's the very first thing I calculate when it comes from
Yes.
the width? And what is it? B minus A, right? This dude minus this dude over N, right? This would be the opposite of that, A minus B. So if B minus A is positive, this will be the opposite sign. So if I switch the limits, and these are called the limits of integration. If I switch those, I get the opposite of the original. Okay, I like it. Kick ass. So there's a few questions that just talk directly about that, but then later it's just going to happen. And we just have to remember what this means. Okay. All right, so there's a couple quick little notes. Now let's try, let's see. Let's try, so this is going to be a Riemann Sum. So 2 x for you. But the infinite rectangles. There you go, Jeff. It's a bad spelling day for me. Infinite rectangles. That's how I get out of spelling bad, is I just don't put the whole word. So, if I gave you a problem like this, let's say 1, 2, 3, let's say 2x squared minus 1. But again, as you're doing your homework, if you hit a problem where it says set up the infinite sum and do this, you should have the little handout I had sit next to you, because it tells you step by step what to do, right? What's the very first thing I need to do to get this thing going?
Find x and y.
Yeah, find delta x. Right, so I'm going to approximate this with this thing. So this would be perfect, and we're going to approximate. So what is delta x? What is a and b?
2 over n.
Yeah, so it'll be 3 minus 1 over n, so 2 over n, there's delta x. Right. And now that I made a mistake last time, it's kind of nice that that happened, because now you're going to be extra careful. Right. So why? Now, once I know delta x, what can I set up next? Well, not that yet. I have to first set up xi.
Yeah.
Is everybody so far so good, right? This step is the same as always. Just divided by n, because they didn't tell me what n was, so I just kind of put it in there. This step is kind of new, but it's still the same idea. If I'm going from 1 to 3, I need to figure out what are my xi's. And how do I get to x1? I'm going to start at 1, and I'm going to add how much?
2.
Yeah, 2 over n. And to get to the x second, I'm going to add 2 of these and so forth. So I'm going to add I of these. So 2 over n is how big each step is, and I is how many steps I've taken, right? Okay, I like it. I like it. Now I can do f of xi. And again, this tells you, I need this, I need this, I need this. I mean, that it tells you what you need. So what would f of xi be? Let's solve some more. F of xi would equal f of 1 plus 2i over n. So that would be 2, 1 plus 2i over n squared minus 1. What can I do right now before I throw shit in to my infinite sum? What can I do right now? Simplify. Yeah, I can square. Yeah. So this will be 2 times. You guys do this in your 1 plus 2i over n, 2i over n, 4i over n, plus 2i over n times 2i over n is 4i squared over n squared. So again, before I start working with something, I'm going to simplify it if I can. And if I do this, 2 times 1 is 2, minus 1 is 1. Twice 4i over n, twice 4i squared over n squared. So now I got my parts. I got my delta x I can throw in. I got my f of xi that I can throw in. Okay, so this happens in a lot of mathematics where you construct what you need to do a process. You construct the parts you need.
Do you want to factor out 8 over n before you plug everything, do the I stuff or
I can't,
no? Oh,
yeah.
okay.
If that wasn't there, even then yeah. You want to first set up these sums and then you can work with each one. So what will this look like now? This will be the limit. And goes to infinity. Add up all my rectangles. F of xi. And then Jeff delta x. Last time I just gave myself an extra I. I thought that'd be cool. A little third I. And now of course you see, what can you do? What can I take out right now? 2 over n. I could, yeah. And again, there's a lot of different ways to do this. And I can break each sum up, right? So I just took that, bam, 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 and then I took that out of all. So just GCF, and then just reorganize my sum. I'm summing up a bunch of sums, so I can do them any order I want to. Now be careful, this doesn't distribute, but doesn't it look like it does? But it's not really distribution. I don't know if you guys get it. It's not even that big of a deal. All right, let me stop for a minute. Everything I've done so far isn't crazy difficult. Why did I take that there? Why was I allowed to take that there?
It's multiplied to all of them.
True.
It's not in terms of the, like.
Not in terms of the variable of this, right? So that's why I couldn't take it out here, because, oh shit. I could take the 2 out, but my God, keep some shit together. This is what I mean, there's a lot of different ways you can do this, but they're all end to the same place. Now we can focus on each of these. Right, each of these guys. What's the sum 1 to n of a constant? That constant times n, right? It's the definition of multiplication, really. It's just repeated addition. So this is n. Woohoo! What can I do here?
Take out 8 over.
Yeah. And then I get this. Let me do this in more steps than normal. And here I can take an 8 over n squared out. So this kind of problem, every single step is not difficult, it's just long. It's just a long process, so thank God we don't do it for very long. All right, let's see, 2 over n plus 8 over n, who's got this? What's that shortcut that Gals went and did just to mess with his teaching?
N times n plus 1 divided by 2.
A lock it. Plus 8 over n squared, and then what's this one? It's not what you hoped it would be.
N times n plus 1 times 2n plus 1 divided by 6.
Yeah, of course, right? It's only obvious. No, it's not. And again, that step is just, I didn't really prove them, but I showed evidence of why it makes sense. And now we've got those. The book actually in the back, the appendices, shows you the proof. It's called Math Induction. Mathematical Induction. It's one of the coolest things ever, but it sounds like a dental procedure or something. You gotta go in for my induction. Yeah, I don't know. So now what do I do? In what way? What's kind of in the wrong place, sort of? What do I need to, should I take him and put him in? What do I get in the first place here? Bam, bam. No. The ends cancel. Plus, let's see, let's do some stuff. 4, right? Is this cool if you guys, is that cool? Right? And then I can bring the 2 over n in, so it'll be 8 n plus 1 over n. What can I do over here? I can there, there. I can kill one of these, right? Right. And again, you don't have to do the simplification I just did. You just bring the shit in, and then you simplify. It doesn't matter, right? So 2 over n times 4. So on the top I get 8, n plus 1. 2 over n, 2n plus 1. On the bottom I get 3 n squared. What tells me I'm on the right track? This is beautiful. This one, what tells me I'm on the right track? The degrees are the same, right? So again, that mistake I made was kind of nice. I will not say that I planned it. It's a complete, honest mistake. But I'm almost happy I made that mistake. And this, of course, the top would be squared, the bottom is squared. I'm on the right track. The limits will come out finite. So the limit of 2 is 2. What happens to this in the limit? What happens to this when n gets really big? Goes to 1. I like this. That's plus 8. And what happens to this?
Goes to 8
No. What's the coefficient on the top of your n squared? Isn't it 2?
Yeah.
So 2 to 1. So it'll be 16 thirds. This 2n squared plus shit over n squared goes to 2. 2 times 8, 16 thirds. And then just add that together. 46 thirds, 15 and a third. I think it's 15 and a third. Crazy shit. All right. And how do you check that? If you want to, how could you check it? Plug this in your calculator into Y1 and then do second calc number 7 from 1 to 3. You should get 15.3 there. All right. And just to remind you guys, I'm going to erase this part. Is that all right? This is what we're about to prove today. What's the antiderivative of this? If this is f of x, what's big ass f of x? Put a 3 there, so it's got to be an over 3, right?
2 thirds.
Yeah. Okay. Minus x, right? Plus c. What is f of 3? Let's see. F of 3 is nice because it'll be 3 cubed 27 over 3 is 9 times 2 is 18 minus 3 is 15. What is f of 0? I'm sorry, 1? 2 thirds minus 1 is negative 1/3, correct? What is f of 3 minus f of 1? 15 minus negative 15 plus 1/3, 15 and a third. This is what we're going to prove today to shortcut all of this, right? Well, we got to prove it first, obviously. And you guys are like, why? Because it's too bad. Okay. So there's no intuitive reason why finding the area should have anything to do with the antiderivative. That's not an automatic thing. There's no, of course not. So we got to prove it. So that's what I'm going to do now, as long as there's no questions from all that. Yes?
So for that last step where you had when you got 16 over 3, I thought the coefficients would be like 3n squared over n squared. So wouldn't that be 3 and then times 8 thirds?
3n squared? No, come on. If you multiply, you get 2n squared.
That's 2n.
Yeah.
Okay.
All right, I'm going to erase all this. So let's prove this then. First thing I want to do, so now we're getting into 5.3, if I remember correctly. Yes, 5.3. This is the fundamental theorem of calculus, part 1 and 2. Heretofore affectionately known as F top. Right? I like it. So a couple things to build us up to this point. Let me ask you something. I'm going to set up something a little bit weird, but it's going to help us understand something later. Let's say that, so some notes going in. If I say f of x equals, this is a little bit weird, so I got 2x, ooh, and let's say that I say g prime of x is f of x, right? Let's just say this is true. I have some other function g whose derivative happens to be this function, yes? So let's put that in. So g prime is 2x, so then what is g? X squared plus c. And tell me this, if f of x is 2x, how does this relate to that? That's little f is 2x, so x squared plus c is big ass f, yes? Is that all right? It's the antiderivative. Now this is a little bit contrived, but I'm trying to make the point that, let me put this here. Let me make this a little bit better. There we go. So what I'm trying to say is anytime, I could have put any function, the same shit would have happened. Anytime the derivative of something is a function, then the g function itself is the antiderivative of that. That's going to show up in a minute. So hopefully this kind of makes sense. If the derivative of something is something, then the antiderivative of something is that original function. That's amazing. But we just haven't written it like this yet. Okay, that's one thing. Oh, that's the only thing. Beautiful. So then we can jump into. So we're going to look at F-Talk 1 first. Fundamental Theorem of Calculus. Part 1. So what this focuses on is if I define g of x to be that funky ass thing that we did before, the weirdest function we've created yet. Can somebody tell me what that function does? It's the function's job. If I plug a value in for x, what does it find?
It's the area from A to.
Yeah, the area under this function from a to that number. Right? So for every number I could plug in, this value could change. I like it. So what's the actual variable over here? What's the actual variable? X. It's the only variable. Okay, I like it. So I'm given a function, I'm just calculating the area at some different stopping place. So that's what can change. The function is kind of like a constant, which is weird to us. If I'm just given a function, I can change the output by changing how far I go. Find the area. Okay, I like it. So what I'm curious about is, let's put the WTN. What is g prime of x? So we've created a function, correct? And what's the very first thing we kind of built up to in this class is given a bunch of functions, what is their derivative? What's the derivative of them, right? And thankfully, all right. We're going to build our way up. This is going to be easier than it sounds. So I'm trying to take the derivative of this thing, yes? That sounds crazy. Well, let's do it visually. Instead of, you want to do the limit definition of? To be honest, we will, but we're going to back into it accidentally, so we'll see what happens. It's kind of cool. So I'm given this function f of t, right? There you go, Jeff. And I'm going from a to x, right? What would g prime of x, bless you, what would it mean? What would g prime of x mean? What does g mean again? What does g tell me? Tell me one word. What does g tell me? Area, beautiful. So what would G prime mean? Change in area. As I change x, right? So if I put this in notation, it would be dg dx. How much does the area change as I move in the x direction? So let's just do it. Let's just freaking do it. Let's move in the x direction a little bit. How do I define a little bit officially? If I want to go a little bit, don't say dx, don't say delta x. Go back to the limit definition. How far up do I want to go? X plus h. I love it. Let me stop for a minute. So I really want this to make full sense. G is the area. G prime would mean the change in area as I move in the x direction. So let's just do it and see what happens, right? So if I go here, how much area did I pick up? Because that would be the change in area, correct? What would the new area be? Well, let's see, what is this in symbols? Isn't this g of x? So what is this in symbols? G of x plus h. Now, how much area did we pick up? Do you see how that's a rectangle? Right? Stop for a minute. I want to figure out exactly how much area we've picked up. So I want to know what this is. How wide is that? H, beautiful. How tall is it? Now this is a little bit of a, I've got a few options here. How tall is that? Well, let's say it's f of x plus h tall. Is that cool? So that rectangle. And what is h again? H is going to get really, really small. So does it really matter which side? Sort of like the left and right endpoint should. Does it really matter what no. So I'm going to pick this side to be the height, because it's going to eventually become 0 anyway. Maybe. So let's gather everything we just did. This change in area. So that would be g of x plus h minus g of x, yes? If I take g of x plus h minus g of x, it has to equal this area, doesn't it? Because that's the excess area now, right? That's the area I've been tacking on. And what is the area of this rectangle? Do it. Yes. So this has to equal f of x plus h times h. Really? Right? So this minus this must give me this, doesn't it? This minus this leaves me with this, and we can frickin' see what this area is. It's just f of x plus h times h. Okay, now watch. This is what I meant by we're going to fall into the limit definition. Sort of going to just tumble into it. We didn't want to do it, and suddenly it did itself. We're like, what do you think? Right? Does that look familiar? What would I do to both sides to get what we want to show up? I'm almost there, right? What has to happen to this to make it become this? What's it missing? I gave it away a second ago. What do I want to let h do to make it become the actual g prime? What do I want to let h do? I want it to go to, take the limit of both sides. I love you guys. I love you guys. Is that cool, right? Because the h's cancel, is that? So what's this? G prime, yes? And what happens when h goes to 0 there? It becomes f of x. Don't you soak that in. That currently, right now, doesn't mean a lot to us yet. That is neat though, isn't it? I mean, the derivative of this funky ass looking thing is just f of x. So immediately, watch this. Okay, yeah, we're going to do something in a minute, but right now, immediately I want to do this with you. If g of x is the integral from a to x of sine t dt, what would G prime be?
Sine.
Yes, because what's f of t? 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 Sine t. And what did we just say G prime is? F of x. So what's f of x? Is f of t is sine t, f of x is sine x. So what this means, let me try to bring this back to us. A lot of shit happened here, right? Has everybody got this as much as they want? Let me make this specific. So if I have sine t, and I'm going from a to x, and I go an infinitesimal step up from here, how much area will I add? Well, sine x. The function evaluated at that spot. That's about how much area I'm going to add. So the change in area is sine evaluated there, because that's how much I'm going to add. It's sort of like the same idea. If I put a thing of tape right here, didn't the area just get the smallest bit bigger? That tape is sine x in this case, right? Okay, maybe. All right. Let's do another one real quick, and then I'll do the little side note here that makes this more impressive. What do you got? So let g of x equal integral from -2 to x natural log of tangent of square root of t minus t dt. What's g prime of x? What does a mean here? What does a mean? I mean, in this specific one, in general, it's a constant, but yes. So in this case, I'm telling you what a is. So as long as this is a constant, we don't care. That's there, right? What's the beautiful thing about this derivative is, how do you calculate? Do you have to actually do the integral? No. What's f of t? This shit, right? So what's the answer? ln of tangent of square root of x minus x. So what we're saying, what does it look like happens when I take a derivative of this? Doesn't it look like the derivative kills this? Right? So it seems to be the opposite of this. And what would this have to be if the derivative is the opposite of it? It would have to be the anti-derivative. Big ass f kind of thing, right? So where does big ass f come into this whole thing? Well, remind me, what did I say earlier about this? What does it lead to? What's that note I gave us? I know I said 2x and x squared, but what's the main idea of g prime equals f?
G of x plus c equals big F.
G of x plus c equals big ass f. Which means this is the antiderivative, basically, right? Which means this is g, correct? So this is the antiderivative of this function. Maybe. I love you guys so much. Now, again, a lot of this is just proof of stuff, right? These are concrete examples of what you're going to see in the homework. These two. Now we're going to do. Now this is a very basic kind of silly thing, to be honest. You're going to see a few of them. This is not the big thing. The big thing from FTOP 1 is that the integral is the antiderivative. That's huge. Why is that so huge? Didn't we calculate antiderivatives of almost any function we've ever seen? Section 4.9. So now that I've said this is the antiderivative, I don't have to do the whole infinite limit shit. I can just calculate the antiderivative. The next thing we have to do is exactly how do I use the antiderivative. We can get it, but exactly how do I use it? So that's the next thing. And guess what that's going to be? FTOP Part 2, I love it. So let's do that. Oh, actually, one more of these. Is this, I don't know, I'm not really numbering these. One more of these. You're going to love this. I know you will. Just put something not too crazy. Sure, Jeff. I like it. You notice anything wrong about the setup of this function compared to what I need for the thing to work? Yeah, the bottom should be the constant, correct? And what did we talk about the first thing today? One of the 3 things I put up on the board. If I want to switch the limits, what do I have to do?
You have to make it opposite.
Put a negative. So this equals negative. Can anybody see another problem? Not problem, but just thing to be careful about.
Squared.
It's a squared on the x. So what's the inside function of this x? Would a chain rule happen here? No. What's the inside function here? X squared. Will a chain rule happen there? Yes. So what does this look like? Let me see. So we have a basic, given this, we have a basic derivative rule. This guy's derivative is the function evaluated at that interval. Why is there no chain rule? Because what's the derivative of the inside function? 1. So like any basic derivative we know, if there's more shit inside, chain rule comes into play, right? So the one we got right now is this. So the basic rule for the derivative is plug that in, yes? So this would equal negative tangent x squared squared, right? Plug that in, that's the basic rule. And then what's chain rule say? Times 2x, chain rule, it gets a term. So that's not different, that's the same thing. Whatever is here is inside the function, yes? Because it's a function of x, whatever is there is inside of it. So the minute that's more than just x, chain rule is going to come into play. Same with any function. This is just a funky function. So just to clean this up, put that out front. Bam. Okay, so it's just like any other derivative rule. We created a new function, it's got a derivative rule, there it is. Chain rule comes in, product rule comes in, yeah, there. Okay. So, this is not the useful part yet. F top 2 is the crazy useful part, right? So what does F top 2 do? Gotta keep myself straight. There we go. So, I want to investigate what this is. I want to know what that is. In fact, I want to prove that this is equal to what we've been doing. We took the antiderivative and evaluated at B minus the antiderivative evaluated at A. We did that a few times and it worked each time. That's not a proof. We could have just got lucky. So we're going to prove this. And just to remind you, what's the power of proving this? You will then be allowed to do this one step instead of delta x, xi, f of xi, plug it in, do the thing, find the thing, do the limit, sum of I squared, oh shit, oh shit, right? Okay. So, let's prove this. Let's see, okay, so let me set up a few things first. We know that g of x, let g of x equal the integral a to x, f of t dt. So we just start. Let me set a few ground rules down. Can anyone figure out what g of a is? We talked about this first thing. If I plug an A in, 0, right? It would be the area from A to A. Yes? Like put an A in. A to A, that's 0 area. No width. And what is G of B? You can't figure it out. What would it? Just put a B there, right? So G of B would be this. Which is basically what we want. Interesting, right? It's basically the same format. So this is just laying some ground rules down, some observations. This is the function we want to use to go in that direction, and this is some stuff that happens to be true about that function. Okay. Now, can somebody remind me? G of x. Remember what we got earlier? G of x plus c is f of x, right? That's the result we got from f top 1. And that's actually my own second step to f top 1. They don't show that in the book, but that's got to do. So what is f of b? Don't overthink. Don't overthink. What would f of b? G of b plus c, right? All right, right. What's f of a? G of a plus c. Crazy shit, right? Okay. So what is f of b minus f of a?
G of B plus 2C. Oh, no, minus.
Yeah.
G of B.
What happens to the c's?
They cancel out.
They cancel.
It's
G of b minus G of a, yes.
I thought you said G of A is 0.
Exactly. Stop. Get out of it. What did we say G of b was? This here, right? Is that cool? We said G of b was this. So anytime I see G of b, I can put this, yes? And like Ricardo said, what is G of a? 0. Now here's the part you have to really just T in this problem denotes this axis, yes? I can call this axis anything I want to. What do we normally call this axis? The x-axis. So this is the same thing as so we've just proven that a problem in 5.2 that I would have had to set up the limit is equal to infinity, summation, blah, 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 it would have looked like this, right? They would have said 1 to 3, like the very first problem we did, 1 to 3, whatever, the 2x squared minus 1, right? And we had to set up the whole thing. Now, I could just take this function, figure out its antiderivative, and then plug these in and take the difference. I don't have to do the infinite limit of the sum of I and xi and blah, blah, blah. Right? I really hope you guys are semi with me. We just did a lot. What we did basically was like so many years worth of work by old math people back in the day. They were young, but they were old relative to when they died, poor guys. Okay, so let's do a concrete problem. You want to do a concrete problem? Okay. So if they ask me now to do evaluate the following, and let me use the technical term, definite integrals. A definite interval just means it's got limits. So obviously we're going to have to talk about 5.4 is all about indefinite integrals where there are no numbers here. Okay. So if I have to do, for example, interval, yeah, let's do this. No, it's not. We already did that. -1 to 4. You got it, Jim. Make something. 3x squared minus 2. What's little f in this problem? Little f of x. This guy, right? That's little f. So now what's big ass f? So that would be the what?
Yeah,
antiderivative, right? Section 4 now. So what's the antiderivative of 3x squared? Why is that nice?
X.
3 just goes back up, right? Minus 2x.
Or C.
Now, with definite integrals, what's going to always happen with the c's? They're going to cancel. It's not tradition, it's convention. Not tradition. No, it's convention to not put the plus c here, because it's going to cancel anyway. It's kind of unfortunate because the minute you guys start to learn this, you forget to plus c when there is no limits. Okay, I like it. So that's this. So how I would do this problem is I would say the integral negative 1 to 4. Let me show you the real way you should do this. This equals x cubed minus 2x, and let me show you the notation we use. Evaluated from what to what? What do I have to evaluate that from? Negative 1 to 4. And the way we show that is evaluated from negative 1 to 4. Why is this symbol not there anymore? This symbol here, why is it not there anymore?
You took it out.
Second? No, go ahead.
Oh, because you took it out with the
Yeah, you did it, right? It's sort of like, would you say, what's wrong with this? If a student wrote this, what would you tell them? What did they do wrong? The screwed symbol should be gone because it did its frickin' job, yes? So why is this symbol not here? Because this is one symbol, that's why. This with this is one symbol. So if you write this and you don't have this, you're wrong. Yes?
So then that, the symbol with the 4 and 1, the line is just like...
Yeah, it just reminds me the limits. I gotta do this. So the way I read this is evaluate this from negative 1 to 4. And the way you do that, you plug a 4 in. What do you get when you plug a 4 in? 64 minus 8. Minus, right? So that's f of 4 minus, and now we gotta do f of negative 1. So what do you get when I put a negative 1 in? Negative 1 plus 2. How much board space? Haven't I used very little board space, and some of the shit is just extraneous shit, right? So, and remember how long it took us to do the limit, infinite, limit, sum, yeah. And we're basically done. Now all we gotta do is do this. 64 minus 8. 56. Minus 1. How would you check that? Put that into y1, do second count number 7, negative 1 to 4. Okay. Is that cool? That's gotta be cool. Right? If you said no, then I would say, okay, you have to do the limit and go to infinity. So figure it out, this is infinitely cool. Alright. So here, you guys, let's see. Do I want to give you this? Sure, why not? Let's do a couple more examples before I throw this one at you. What about, all right, yeah, let's do this because this gets interesting. Now, what could help you out, and what I want to remind you, what does that symbol mean again? Okay, sure, area, but what's it come from? It's a big ass S, right? Because it's taking the place of the what symbol? Sum. So this is a sum. A sum of things that all have 2 in it. So could I take a constant out? Right? Remember we basically did that when we did the infinite limit thing? So if I wanted to, any constant multiplier can just come out. You don't have to do that, but I thought maybe this would help you do this, right? So that's asking you now. This symbol we now identify as, sure, it's area, but it's antiderivative. So you think to yourself, what do you take the derivative of to get 1 over x? Okay, be very specific. What's wrong with this? Anybody remember? And now you see why, right? Remember that? We talked about why it's got to be absolute values so the domains match? Because can 1 over x handle negative numbers? Can 1 over x handle negative numbers? What's the only number it can't handle? 0. So my answer better be able to handle negative numbers also. Otherwise, how could that represent the area under that, which definitely exists? Yes? Does that make any sense? A little tiny bit. And I want to evaluate it from -5 to -3. So I just got to plug it. I'm going to throw in the calculator because I don't know what natural log of 3 is, right? So it'll be 2 natural. You always do the top first, which is like our quotient rule song. Top first. Okay. Top first. Right? That's the value of that. Minus. Plug in the -5. And then you go whatever. You get some. Oh my. I'm not even going to try to guess. Sure you are, Jeff. I'll say 0.37. Negative. I don't know. Is anybody doing that? Thank you, guys. I am probably wrong. I am fine with that. Is anyone doing it? Are you worried about your answer? I don't know. It should come out negative. If I'm thinking about this right. What's it come out to be?
Negative 1.02.
All right, I was way off. I can't think of natural logs in my head, so I don't. Okay. Why is that okay? It came out negative in this area. We're cool with that, right? We're calc people. We're cool with negative area as long as it's not a physical thing I can hold. Then it can't be negative, right? I'm not losing triangle. There's a negative area triangle. My triangle. I don't know. All the triangles in me are being stuck. I don't know what that means. But purely mathematically, negative area is fine. And physically, again, it could be the loss of money, the loss of whatever, water flowing out of something instead of in, right? Okay. So let me give you this. Oh shit. So don't worry about the side that's from 5, 5. We're not in 5, 5 yet. Most of us. Hey, the other side might help you tomorrow. So just try the first one right now. Oh, basically what we just did. Almost. Almost the same thing, that's funny. So what is the antiderivative of this?
X plus X.
Is that cool? X cubed plus X evaluated from -1 to 3. So when you throw a 3 in there, you get who? Careful, cubed, right?
Oh, cute.
27 plus 3, 30. Minus, now here's one little thing, you guys see this? It's got to be f of b minus f of a, right? So be careful, you got to have a minus and then the actual what it is when you put a negative 1, and when I put a negative 1, I get negative 2. So 30 minus negative 2, check, is? Holy shit. Then again, put that under y1, second count, integral, negative 1 through 7. Alright, so try part B. Yeah, that should be. And again, the better you are with derivatives, the easier this will be. You just gotta think backwards. What's that, guys? Antiderivative. Tangent. I love it. From 0 to pi over, let's say 4. Yeah. So now tangent pi over 4 is 1. Tangent is 0 is 0. That's neat. Secant square is a funky ass looking function, and when you do from 0 to pi over 4, the area you get is 1. That's kind of neat, right? It's a weird ass thing. Alrighty. Part C we basically just did, but it's got a little twist to it. So try part C. What's the antiderivative of this? Good. So when I put a negative 1 in, of course it becomes 1. Minus twice natural log of e. What's natural log of 1? 0. And what's natural log of e? Yeah, they cancel. You guys know, you guys, right? I mean, the funny thing is, I mean, this stuff, you're like, I love it, because what we do right before this is long, so I mean, you have to love this, especially relative to that, right? Now here's where things get interesting with remembering derivative rules. So again, you're always asking yourself, well, what would I have taken the derivative of to get that? Because this is trying to undo the derivative. Get the test back. What you're gonna do? Your eyes. Okay. Who thinks they know the antiderivative?
Is it 3 to the power of x?
Is it? Right. Any exponential is basically based on itself, right? The derivatives are based on itself, so the integrals, the antiderivatives must be based on themselves. So it has to be 3 to the x. And then the derivative of 3 to the x is 3 to the x natural log of the base, natural log of 3. You guys see that? So again, that's one of the more obscure derivative rules. We don't really use it a ton, and it's weird. But it's exactly why e to the x kicks so much ass. Because natural log of e is 1. Yeah. So this antiderivative is 3 to the x. We now want to evaluate it from 2 to 3. What's 3 cubed?
What do you say?
3 squared.
9.
Crazy. Crazy sauce. 11.
So what was it that happened to natural log of 3?
Say again?
What happened to natural log of 3?
So remind me, what's the derivative of 3 to the x? What's the rule? What's the derivative of e to the x? E to the x. So that's a number to the x power. So everything that's a number to the x power should be related to that. This isn't e though. The real definition, let me just put an a here. Any number to the x power's derivative is itself times the natural log of the base. The natural log of the base was the modifier if it wasn't e, because e is the only function who's its own derivative. If I don't have e there, it's got to multiply by the little modifier. That's the way I look at it anyway. So the antiderivative of anything to the x, natural log of that thing, is that thing to the x. Right. Now, what do you have to be careful about with part e, with the e, part e, and the e? Why is this when you got to be a little careful about the antiderivative? Because it's not just e to the t, e to the 3t. So you just got to be careful. So the answer's got to be something related to e to the 3t. We know that because it's an exponential. So it's got to be this. But what would this guy's derivative be?
3.
And there's no 3 there. So what must have been there before? 1/3, right? It's the same idea we saw before, right? That's the thing I was talking about before. There's a chain rule piece. There would have been a 3. There is no 3. There must have been a 1/3. We're going to learn a process in 5.5 that we could use there, but when it's just a constant, who gives a shit? You can kill it, right? It only matters if it's a funkier function. So there should have been a 1/3 there, and you could check yourself. The derivative of this, 3 would kill that, e to the 3t, beautiful. Now you see why I made the limits natural logs, because, well, let's see if you guys are able to handle this. This will be 1/3 e to the 3 times natural log of 3 minus 1/3 e to the 3 times natural log of 2. Now before you go reaching for your calculators, you could do something. Doesn't that e want to kill that ln? Don't they want to kill each other? They hate each other. What's in the way? 3. And he's like, oh shit. So he gets the hell out of there. He's like, I don't want to get in the middle of this damn thing. No, whatever. Right, so this 3 can come up. You guys remember that? Logarithms? The coefficients can come back up as powers? Yes? That's a basic thing about logarithms. So this will be 1/3 e to the natural log of 3 cubed minus 1/3 e to the natural log of 2 cubed. So the e to the natural log kills each other. 1/3 of 3 cubed is 9. 1/3 of 2 cubed is 8/3. And 9 minus 8/3 is 19/3. I love it. 6.338. So one thing you have to realize, I mean, this is not a lot of work. It really isn't. Especially compared to the infinite rectangles approach, right? My God. So thank God we proved that finding the areas are related to antiderivatives. That's so kid-based. One little thing I'll say is indefinite integral. So this is actually section 5.4. When you have an indefinite integral, you just find the antiderivative. That's all that means. It's just, if the definite integral is find the antiderivative and then plug the numbers in, and if there's no numbers to plug in, that just means find the antiderivative. So what would B be, for example?
Zero.
No. Not find the derivative, find the antiderivative. I know it's a pi, who cares? It's a number.
Pi x.
Nah.
Pi
Pi t.
Oh.
And you're almost right. You're almost right.
plus C.
There it is. Why is there a plus c? Because it doesn't cancel, because I don't have limits to make a minus. There's no subtraction that would make the c's cancel. This is where students start to forget the plus c, and I really can't blame you, because the definite integration, you don't put plus c, because they die. And then you're like, I forgot. Cool. Yes? So that's not too bad. So we'll finish this up next time. On the back, if you want to, you can look ahead to 5.5. This is integration's answer to the chain rule. And real quick, before I forget, let me do one little thing. Just do it here, Joe. If somebody does this, for example, x times sine x. All right. If somebody please, all right, let me just try to nip this in the bud. If somebody says this, how many guys are cool with that? I think with my tone, nobody should say they're cool with that. Right? I think you picked up that this is wrong. What did this person do? And maybe some of you guys are like, I don't know, this person did great, I thought. What did this person do? They just took the integral, the antiderivative of each piece, right? Would you agree with me that antiderivatives are worse than derivatives?
Yes, sir.
If I was going to take a derivative of x sine x, wouldn't I have to apply the product rule? Yes? So if I'm going to take the integral, the antiderivative of a product, that has got to be disgusting. That has got to be gross as shit. I need you to understand this. We don't know product rule for integration. In fact, there is no product rule for integration. There's integration's answer to product rule. So like I call this integration's answer to chain rule, the other side, right? So you gotta, I know I couldn't do the derivative like that, so I definitely can't do an integral that easy. It's not gonna be, in fact, you're not gonna know how to do that problem this semester. You would learn how to do the problem next semester. If you did Calc 2, by the way. So if you don't do Calc 2, you'll never know how to do that, and some of you guys are like, I can live with that. Okay. Okay, that's it. I'll let us out a little early. Why not? Let me know if you have any questions. Otherwise, have a good weekend. What's up? Oh, yes.
I have the study tomorrow.
Huh?
I have the finals for tomorrow.
Final?